I showed you the playground last time for a simple example, but this time I want to use it to demonstrate the most important elements of the Marlowe language. And as I mentioned last time, there are different ways to actually write Marlowe contracts, and we'll look at those two, JavaScript or Haskell, in more detail in the next lecture. But in this lecture, I want to concentrate on these two, typing Marlowe directly or using Blockly. And arguably the nicest way, especially for beginners, to get started with Marlowe is using Blockly, where you can assemble your contracts by mostly using the mouse. So you don't have to type any code with the keyboard. So the arguably most simple Marlowe contract is the one that just closes. So if we send that to the simulator and start the simulation, it immediately ends and nothing has happened. So that's quite boring. So let's go back to Blockly. And the concept of Blockly is that you have this contract. At the moment, it's just closed, but let's remove that now. And you can fill in building blocks into these holes here. And there are various types of blocks, and the holes are shaped accordingly. So basically visually you can see what you can enter in various holes. So let's start very simple by writing a contract where there are two participants, a giver and a receiver, and the giver sends 100 ADA to the receiver. Now, of course, in order to do that, you wouldn't need Marlowe. You can just use your wallet. But nevertheless, let's try to do that in Marlowe, and maybe it's a bad example because in Marlowe it's actually more complicated, much more complicated than it would be to simply use your wallet. But of course, Marlowe offers many features that then make things very easy in Marlowe that are impossible or at least very difficult to achieve with other means. So if we click here on contract, this pops up and that tells us what we need to fill this hole. So if we click on base contract type, then we will actually get the contents of this menu item here, but let's click on it. So we see we have 1, 2, 3, 4, 5, 6 options to fill this hole. Close we already saw, so that's boring. So let's look at the other 4. Actually, assert we will also ignore. That will probably be deprecated soon. So the interesting ones for us are those 4. Now pay looks promising because we want to do a payment from the giver participant to the receiver participant. However, we can't use that directly because payment in Marlowe always goes from an internal account to either another internal account or to a wallet. I mentioned internal accounts before. So the concept is that in Marlowe, each participant also has a so-called internal account. So I briefly explained last time that the state of a Marlowe contract is represented by a UTXO on the blockchain, an unspent transaction output, and that UTXO contains some data, but also value. Can be ADA, can be other tokens. So internally, there's some bookkeeping that says how much of that value contained in the contract belongs to what internal account, and each participant has one. I mean, the value is all lumped up in this UTXO, but the data associated with the UTXO keeps track of to which internal account how much of the value belongs. And payments, so this here, this pay, can only originate from internal accounts. So if we want to make a payment in Marlowe, we first must get some funds into an internal account. Now, that means we need the giver to make a deposit into the account. And that is something the contract can't enforce. I mentioned that last time. There are actions that the participants of the contract must perform, and you can't force them to do that. And for situations like that, when you expect one of the participants of the contract to do something, we need this when construct. So let's use that. And let's see whether it fits into this hole. It doesn't look as if it will, but actually it does. So this hole just gets bigger. And now we see that we have more holes. And we have to set a timeout. I also mentioned that last time. That is a very important concept in Marlowe, that everything has a finite time. So no money can be locked in a Marlowe contract forever. And this is enforced by insisting on timeouts for when clauses. So we see there is constant timeouts and also parameterized timeouts. When we give a constant timeout, we, as the name suggests, must give a constant time. So let's try a constant first, and let me just pick something far in the future so that I don't have the issue that when I actually try the contract, the timeout lies already in the past. So let's just pick something in 2023. Let's say 1st of January 2023. The time doesn't matter. Okay, so that's the first thing. Now we have these two more holes, and if I click here on the when, I actually see the types of those holes. So I need case and I need a contract. So what does that mean? Case is what actions from participants I'm waiting for. So in our case, that will be a deposit because I'm waiting for the giver to make a deposit into the contract. And then this continue as, the contract is what is supposed to happen when the timeout is hit. So if none of the actions I'm waiting for here happens, then the contract will continue with this. And here I can simply do close. So let's click on this and choose close. And let's put that in here. Okay, and now for this part. So I can again click on the when if I want, and then here on case, or I could immediately click on actions. So there are three. Notification is a special construct that's not used very often. So we'll mostly look at deposit and choice. Let's start with deposit. Slot that in here. Now we see we have lots of new holes. So we have to say who is to make the deposit, how much, in which currency, and into which internal account, and what should happen afterwards, after the deposit is made. Okay, let's click on this so we see the various holes here. So first, who is supposed to make the deposit? That's a so-called party. So it represents a participant to the contract. And there we have two choices. We can give a fixed party by specifying a public key or public key hash, or we can pick a role. So let's do this, and we can give it a name. So let's call it giver. So the giver has to make the deposit. Now how much? I think I said 100 ADA. So we need a value here. There are lots of options. So you can do arithmetic with values. So given two values, you can add them or multiply them and sorts of other things. But in particular, there's also this constant here. So I can use that and say 100 ADA, but actually this will be loveless. So I should say 100 million. 123, 123. Now the currency should be ADA. I click here on token. I could either specify a native token with policy and token name, or I can choose the special case ADA, slot that in here. Now into which internal account? So let's say into the giver's internal account. So again, a party and giver there. And finally, what should happen afterwards? So once the money actually is deposited, I can do a payment. So now I need another contract. So now this pay contract makes sense. So payee is who is getting paid. And there now I have two choices. Account off would be an internal account, or I can make a payment to an external wallet. So that's what I want in this case. So I use this, and I have another hole. I must now specify a party again, and this will now be a different party. That's the receiver. Now I must say how much, and again, token and from where it's supposed to come. So I can replicate what I did there. There are other options. For example, let's just for variety's sake, for value, let's not use constant 100 million this time, but use this value construct, available currency from account of. So I just say everything from the internal account of the giver. So available currency. So this is now token ADA from account of party giver. Oops. Of currency ADA from account of party giver. And finally, what should happen after the payment? Well, then we are done. So actually I can also copy paste. So Control C, Control V copies this, and I can put the close in there. So to recap, what does the contract do? It's a when. So if none of the actions specified here happens until the timeout specified here, we immediately close. So nothing happens. If one of the action happens, in this case, it's a deposit from the giver, constant value 100 million, ADA, to his own internal account. Then we'll make a payment to the external wallet of the receiver. Value will be the available ADA from the giver account, which in this case, at that point, after the deposit has happened, will be 100 million. ADA from the internal giver account, and then continue with closing. So let's try it out. Send to simulator. We can specify the initial time. So by default, that will be set to now. So this is when I'm recording this video, and I can start the simulation. So if I don't do anything and wait until it has expired, then nothing will happen. If, however, the giver makes the deposit, then we see giver deposited 100 ADA from his wallet into giver's internal account, and then the contract pays 100 ADA from the internal giver account to receiver wallet, which is what we wanted. Another way to write Marlowe contracts is not to use Blockly, but to use Marlowe directly. And this is actually not as complicated as it sounds, because there's a lot of support in the editor to help you get the syntax right. So for example, if I just type a W, I get when and all the other constructs I can use at this point. So let's do when, and I get these two holes for the timeout and the contract that should happen if the timeout is hit. And I even get this quick fix button here. So when I click that, I get the two possibilities for the timeout, the absolute value or a parameterized value. I chose the absolute value before, but let's now do a parameterized value. So I can give it a name. Let's call it deadline. And now for the continuation contract. So if the deposit is not made, what should happen then? And let's again do this quick fix, and I can choose close. So now here I need my actions, and there it's a so-called case. So we only had one case. We were only waiting for a deposit, but there can be several actions we wait for. So then whichever of the two or more actions happens first is the one with which the contract continues. So we'll see examples of that later. So we need case, and now we can get to hold. So the action we are waiting for and what should happen if that action actually happens. So we're waiting for a deposit. And then earlier in Blockly, so we waited for a deposit of the giver to its own internal account and then made a payment from the internal giver account to the external receiver wallet. Actually, there's a simpler way to achieve the same effect because close is actually not as boring as I made it out to be until now. So one thing that close does is it pays all the internal accounts to their external wallets, which means that if instead of making the deposit to its own internal account, the giver makes the deposit to the receiver's internal account, then if afterwards a close happens, automatically the contract will send that internal value at the receiver internal account to the external receiver wallet. So here we can simply do a close. And now here we do a deposit from the giver to the internal receiver account. So and do deposit. I get a bunch of holds. So party from party. So I never know which is which. I mean, there are two parties. One is the receiving internal account. The other one is the originator of the payment. But in this case, luckily, it's easy because from party, the name makes clear that this is the person or the party that pays. So that should be our giver. So public key or role. So role giver. So then this is the receiver. Token. Here we only get one option. In Blockly, we also got ADA as an option. Here there's only this token option. But as it so happens, ADA is also a native token, a very special native token, where both policy and token name are the empty strings. So just like this is actually ADA and the value. And there we had constant 100 million because it's actually loveless. And that should be it. So we can switch back and forth between Blockly and Marlowe. So this would be the Blockly representation. Of course, it's somehow nicer and easier to use Blockly directly. But when you get more experienced, maybe it might be easier and quicker to actually directly use Marlowe, especially if you know what constructs are available. But with these autofill, autocomplete, and the quick fix and so on, it's actually relatively nice to do Marlowe directly. So let's see whether that indeed has the same effect. And now we have this new feature that instead of a constant deadline, we gave this parameter. So if we now send it to simulator, earlier we just had the initial time, but now we can also specify this parameter, the deadline. And automatically the simulator will set that to 5 minutes after the current time, which is actually quite nice. So we can just take it like this and start the simulation. And now if we do the deposit, then giver deposited 100 ADA from his wallet into receiver's internal account. And then we hit the close. And then because of this behavior of close to pay internal accounts to external wallets, the contract pays 100 ADA from the internal account of receiver to the receiver wallet. So we again get the effect that we got before, that giver deposits 100 ADA and then they immediately go to the receiver without having to use the pay construct. So this was a first simple example of how to write a Marlowe contract using Blockly or using Marlowe directly. And next we will look at some more of the available constructs. Before we look at more constructs, let's briefly talk about parameters, about metadata, and about how to load and save your work. So we were using one parameter in this last example, namely for the timeout of our when clause. So we called this parameter deadline, and then when we send it to simulator before the simulation starts, we have to pick a value for this deadline. or rather one is picked for us automatically 5 minutes in the future, but we could edit this. So timeouts are one place where you can use parameters. There's another one, namely values. So in this contract, there's one constant value, this 100 ADA here. Let me remove that and replace it with a parameterized value. I can give the parameter a name. Let's call it amount. And now if I send to simulator, I can again choose the deadline. And now I also can choose an amount. So if I choose 50 ADA, then instead of the former 100 ADA deposit, now the giver is supposed to make a 50 ADA deposit. If you do that as before, the receiver gets it. So those are the two places where you can use parameters, timeouts and values, constant values. If we go back to edit source, we see down here this metadata tab, and if we click on that, then we can edit the so-called metadata of the contract. So that's things like descriptions, names, help texts. In particular for the contract itself in the top portion, and then for the parties, the participants, and finally for the parameters. So for example, contract type other is fine. Contract name is Marlowe Pioneer Program, simple payment, close. Giver makes payment to receiver. And do the same here, I suppose. We can describe the roles, and we can also describe our parameters. If we try this out now, we see that now our metadata is used here. So for example, here now we see this currency symbol ADA, and now instead of the 50 million, we can just type 50, and this is now correctly scaled to Loveless. Also, here we have these tooltips where we see our description of the parameters. Finally, what we can do is we can save the contract. And when we do that, the metadata that we just entered will be saved as well. So we can go to Save As and pick a name, press on Save. And I mean, as it usually works, once we have picked a name, if we press Save, then the previous saved data of code will be overwritten. So the way it works, it's not saved to your hard drive. Instead, it's saved as a GitHub gist. So in order for this to work, when you do it the first time, you have to log into GitHub and grant the playground permission to create gists on your behalf. And similarly, you can always open existing ones. So if I do that, there's all sorts of gists that I did for previous events. And here are the 3 contracts that I saved that we saw in this lecture. So the simple payment one using the pay contract, then the simple payment one using a simple close, and finally the one where we replaced the 100 million Loveless with the parameter. Here I went to the corresponding GitHub gist page where this was saved. And we see that this gist actually contains 3 files. The first one is called metadata.json, and as the name suggests, it contains the metadata that we just entered. Then playground.marlowe, which is the actual Marlowe contract. And finally, something called playground.marlowe.json, where I'm not really sure what that is for, and it's just an empty JSON object. We will leave the links to all the gists of the example contracts I show you in Canvas. And what you can do is go to that link so you end on this page and then you can click fork. This is now not visible because it's my own gist, but you will see a fork button, and if you press that, then this gist will be forked to your own GitHub gist. And then it will be available to open when you are in the playground. So that's an easy way for you to get this example code and also to share with others. Now let's look at some more important constructs. We can't go through all of them, but if we check contracts, we have talked about when, we have talked about pay. We haven't talked about if and let. So let's use an example that has if, and somehow you can't really do anything interesting if there's no money in a contract. So normally contract will always start with a deposit. So we always start with a when, and then at least one party should make a deposit. Let's say we want a contract where one party makes a deposit and then a second party can make a choice and decide who gets the money from the deposit. Let's start with that. We need a case. Let's call that giver again. Okay, these are all things that we have seen already. So we wait for a deposit by party giver until a parameterizable deadline, and the value of the deposit is also parameterizable in ADA for simplicity, and the giver just pays into his own internal account. So afterwards, we want somebody to make a choice. So this is also an action that we have to wait for. So again, we need a when. So let's actually change this and call this deposit deadline. And then here we need a second deadline until when the person making the choice has time to make his choice. So let's call that choice deadline. If no choice is made, we just close the contract. Okay, so now for actions. We have seen deposit. I said that notification is somewhat special and not used often, but choice is important. So let's now see an example of choice. First, choice has a name. Doesn't matter, let's just call it choice, because we will only have one choice here. Choice owner is the party being able to make the choice. So that will be a new one. Let's call that party chooser. Choice bounds. So choices are always numerical. So it's always numbers. But you can specify a bound. So it's always integral numbers. So in this case, if it's 1 and 2, the only two possible choices would be 1 and 2. Last week, we saw an example where the choice was actually a price, these two prices given by the oracle. So there were millions of or even billions of possibilities. So the range was much larger. But actually now the idea is that this chooser can choose between two potential recipients of the money. So let's just leave it at 1 and 2. Okay, and now the continuation. So if this choice has happened, and now we are in a position where we can use the if, because now we want to branch. If choice 1 was made, we want to give the money to one party. If choice 2 was made, we want to give it to another party. So let's put this if in there. Now we need an observation. So a Boolean value, it can be true or false. If we look at observations, first of all, we see there are logical connectors. So you can combine two observations with logical and or logical or you can negate. You also have like the atomic observations, true, the observation that's always true, false, the observation that's always false. And then there are interesting ones. So these here are comparisons of two values. So one value is greater or equal than another, greater, less than or equal. Finally, we can observe whether a choice was made. In this case, we already know that a choice was made. Otherwise, we wouldn't end up in this if contract. So what we need is we want to check whether the choice value equals 1 or 2. So we know it can only be 1 or 2. So the observation we want is we want to check whether it's 1, say. And if it's not, we know it's 2. So this would be value equality. So, and the 1 value will just be the constant 1, let's say, this. And here now, until now, we've only used constant values, and this one here, available currency from account. But we see there's some arithmetic possible and something with time, so we can observe the current time, and we can use a name that is used in combination with the let contract that we haven't looked at yet. So in the let contract, you can give a name to a value, and then later you can reference it by this name. Okay, but what we want now is choice. And this is now where this name comes in, because there can be several choices. So we called our choice simply choice, and we know it was made by chooser there. Okay, so what will this do? We know we only get here when this has happened, when the choice has been made. And then this choice value made by role chooser can be 1 or 2, because we set the bounds between 1 and 2. So if it is 1, then whatever we put here will happen. And if it was not 1, then this will happen. You know, in this case, the choice was 2. So in this case, we want to make a payment. So this. Okay, and the payee is now the one that corresponds to the choice 1. So, and let's pay to his internal account first. Doesn't really matter. So this is now the party that corresponds to choice 1. Let's just call it receiver 1. The amount, well, that's the amount here that is now in the internal account. The value, we can, for example, use this again, amount. We could also use this available currency again, and it's ADA from the account of, it was the giver, and afterwards we are done. So afterwards we can use a close. Okay, and in the else case, we want to give to somebody else, not receiver 1, but let's call him receiver 2. So let me just copy paste this whole pay block here. And all I need to change is this. We can try it out. Now we see this has already automatically been done, but it's unfortunately the wrong way around. I mean, we first want to make the deposit and later the choice. I mean, we could, of course, now edit that here, but it would be nicer if by default it was already done correctly. And this has to do, if we go back to metadata that I haven't set yet. So let's set some of this metadata now. I think you need to set the metadata for the time parameters for the ordering to work correctly. And actually, you also can change the order of time parameters here in metadata, and that will then later be reflected when you have to enter the parameters in the simulation. So if one comes before the other, then by default, the one will happen 5 minutes before the other, which can of course be changed. But it looks as if they are already in the right order. So let's try this again. Yeah, now it's the right way around. Okay, so now the deposit deadline comes first and then the choice deadline. So let's try it out. We do start simulation. I forgot to set the amount. Let's say, and I probably should set the format for the amount parameter again, so that it's nicer and I don't have to enter the 6 zeros. Let's say 100 ADA. Now we can make the deposit. If we don't, then nothing happens. So let's make the deposit. And now participant chooser can make a choice. And we see here, we can in principle enter other values, but then we get an error. So only 1 and 2 are allowed. So let's first do 1 and make that choice. And the contract ends, and we see here receiver 1, the contract pays 100 ADA from account of receiver 1 to receiver 1 wallet. I could have done that directly. In the pay, instead of using account, I could have directly paid to the wallet. Here now the payment goes to the internal account, and then when the close is hit, it, as I explained before, close always transfers the remaining value in the contract from the internal accounts to the corresponding wallets. So here the choice 1 was made. The contract then paid 100 ADA from the internal account of giver to the internal account of receiver, and then when the close happened, that ended up in the wallet of receiver. If I go back and make the other choice 2, then we see that instead receiver 2 receives the money. So that seems to work. If we look at the possible contracts, we have talked about when, pay, if, mentioned that a third we won't use. So close we have talked about. So the only remaining one is let. So I want to briefly demonstrate let, even though in this case it's not really useful. So as I briefly explained before, with let you can give a name to a value, and then inside the continuation, the contract that comes after the let, you can refer to this value by that name. So there's this one value here, constant param amount, that we repeat 3 times in this contract. So what we could do is take out this when here, put it inside a let, slot that back into the contract, and now give some name like amount, lowercase, to this value here. And then wherever we use this constant param, we can now instead make use of this use name construct and then refer to it by this name amount lowercase. So I can remove these 2 occurrences here and instead copy, paste that in there, the use name. And the behavior should be exactly the same. Now here in Marlowe, it looks like this. So if we send it to the simulator, set for example 50 ADA this time and start the simulation, make a deposit of 50. Let's say we choose 2. And receiver 2 receives the 50 ADA. So now we have seen all the available contracts. We talked about observations, Boolean values that can be true or false. We have seen the actions, deposit and choice, not notification, but as I mentioned, that's quite rare and not very important. Values, and of course we have talked about payee and party and token and also bounce. So now you have seen all the available constructs that you can use to assemble a Marlowe contract. There's one last thing I want to show you here before we go on. Namely, if I run the simulation, let's set it to, I don't know, 70 ADA this time. So you notice that now the whole contract here, this whole when, is blue, light blue. So this is the basically remaining part of the contract. So we already did the let, so we are already in a state where this name amount is bound to this value, and now we are here in this when. Now if I make the deposit, we see that the blue area shrinks. So now this is done. This happened, the deposit happened. So now we are in this inner when, where we are waiting for the choice. So if I now make the choice 1, the contract is done and nothing is blue anymore. Same if I made the choice 2. So we always see the remaining part of the contract, and that gets smaller and smaller until the contract is done. As the last topic for today's lecture, I want to talk about static analysis. So that's one of the great features of Marlowe. As Simon explained in the first lecture, there are some trade-offs being made with Marlowe versus Plutus. Plutus is a general purpose language. In principle, you can do anything with Plutus. Marlowe is much more restricted and it's much simpler. So it means you can only write certain contracts in Marlowe. Not everything you can do in Plutus, you can also do in Marlowe. But the big advantage of that is that Marlowe contracts can be analyzed and they can be analyzed statically. I mean, of course, you can also analyze a Plutus contract, but it's much more simple to analyze a Marlowe contract and to get much stronger guarantees with actually very simple analytic tools. And in particular, you can do this so-called static analysis, which means you don't need to run the contract to analyze it. In Plutus, often when we test Plutus contracts, we use something like unit tests or property-based tests. So property-based tests are much more powerful than simple unit tests. There, the idea is that you generate hundreds or thousands of random test cases, throw them at the contract, execute it, and see what happens, and see that whatever happens is according to your expectations. But in principle, in Plutus, you actually have to execute it to see what happens, to test it. Not so in Marlowe. In Marlowe, you can just look at the contract and analyze it without having to run it. And this is accessible here in the playground. If we go to static analysis, and at the moment we see there are like 3 different types of static analysis that are done that might change in future and be combined in like one big report. So at the moment, this is the contract that we ended with in the last section. So at the moment, there are no warnings. There's nothing with reachability. And if we do the analyze for refunds on close, we do get something. It says the following close constructs may implicitly refund money. And then it lists various paths through the contract. So it says we do the let, then the when first case, that's the deposit, and then the second when, that was the choice times out. So this is the case where the deposit is made, but then the chooser refuses to make a choice. So in that case, there will be a refund. And that's true. And that's also by design, because we want the depositor, the giver, to get his money back in this case. So the second is the deposit is made, the choice is made with value true. So that means 1 was picked. The payment happens and then close. And that's also a fact, because the pay goes to the internal account of the receiver. So when the close is hit, the receiver gets refunded. But that's also by design. Finally, this last one here is if choice 2 was made. And again, then receiver 2 gets the money from his internal account. So as it says, this does not necessarily mean there's anything wrong with the contract. So I did it like that on purpose. We could change the contract. If we change the payment here, and instead of paying to the internal account, we directly pay to the wallet. We can do the same in the second branch of the if statement. Let's just change this to receiver 2. So now, if we do this again, these last 2 cases have disappeared, because then in the case where the choice is made, the payment happens directly to the wallet. So when these closes here are hit, there's no money left in the contract to be refunded. So the static analysis sees that. Now, what about warning and reachability? So let's first look at reachability. Though that checks whether there are branches in the contract that can never be executed, that are unreachable. So in our case, we don't have any. But for example, if I change this observation here and instead of constant 1, say constant 3. Remember, the only 2 possible values are 1 and 2. So this should always be false. So in this case, we should never get into the then branch and always end up into the else branch. So let's see whether static analysis detects that. And indeed it does. And it tells us, okay, If the deposit was made and the choice was made, then true leads to unreachable code, which means the true case is impossible. So it will never be the case that this statement here is true, which is true because we know this here is always 1 or 2, so it can never equal 3. Let me change that back. So that's nice. So when you have something like that, that's of course at least a strong indication that something is wrong, that you made a mistake or didn't consider it. Or in the very least, you can, in that case, remove parts of your code and make it simpler. So if I really wanted a 3 there, then I could remove the complete if statement and just replace it with this else branch, because the then branch would never be hit anyway. So now warning, let's look at an example for warning. Let's say I replace this here. Let me first clear this, sorry. Yeah, okay, I just wanted to check. So I set the amount to 50 ADA. So let's say instead of paying amount, I remove this and replace it with some constant value, let's say 100 ADA. So if I now analyze for warning, then I do get a warning and it says partial pay. The contract is supposed to make a payment of 100 ADA from account giver party to the wallet of receiver 1, but there are only 50 ADA. And it also gives me a sequence of actions that can lead to that situation. So the contract starts, then the deposit is made, 50 ADA, then the choice is made for 1, so choice number 1. And in that case, we would end up in this then branch and then hit this payment here of 100 ADA, but only 50 ADA are there. So it detects this problem that we want to make a payment that's not possible in this situation. If I clear this and put, for example, 150 ADA there and do it again, then we don't get warnings. Because in this case, the deposit, the 150 ADA now, is high enough to cover the payments, to cover this payment of 100 ADA. So this is, of course, just a small example of what's possible. There are other things you could check for. You could statically analyze a Marlowe contract for, but these are already very useful. So you get warnings if there is a payment that can't be made under certain sequences of actions, and you get a warning if there are branches of your code that can never be reached. As homework, I'd like you to write the following contract. It will take 2 parameters, one deadline and one deposit. And the idea of the contract is that we have 3 participants, giver 1, giver 2, and receiver. And giver 1 and giver 2 both have to deposit the deposit amount into the contract. And once they have both done that, all the money goes to the receiver. Ideally, it should work in a way that both giver 1 or giver 2 can make the first deposit. So that would be a case where we have a when clause with 2 cases, 2 possible actions. And depending on who does the first deposit, then the other one must make the next deposit. So to demonstrate here, both participant giver 1 and giver 2 can perform action. If giver 1 makes a deposit, then giver 2 must give the deposit next. And if giver 2 makes the first deposit, then giver 1 should make the next one. In both cases, receiver then receives the total. So in this case, 100 ADA. If you feel this is too difficult to give this option for both of the participants to make the first deposit, you can also do a simpler case where giver 1 must make a deposit first and then giver 2 must make the deposit next. But in that case, you would need 2 deadlines, one for giver 1 and one for giver 2.